Yeah, but
okay, hi everyone. So let's start today.
yeah, that seems so easy. I remember in class you were saying that instead of just focusing on the point at the interval, on steady state.
So are you guys done with homework? No?
It was okay to use the example that you provided, right?
What do you mean?
Because you know you already had everything plotted, but with different numbers that we actually had. What I did is like I reorganized all the numbers. I used your equations that you had already plotted, and then I created the Word file that you suggested for us to upload.
Yeah, always have the Word file because your Word file is
And
the
the one
main
that you
one.
also are going to correct.
Yeah, but have the Excel file as a support of the information you put in the Word file.
Yeah, you have to upload both, right?
Yes.
Okay.
Word file is just problem, solution, that's it.
Talk about how you did it.
Too late.
That's fine. No, that's fine.
Well, I already submitted it.
Oh, you just get one submission?
Oh, I don't know.
So this is what I want to say. If you put time into something, you just want to make sure that the other person understands it, which is the grader. Okay? If you add 2 lines of explanation, okay, it's going to support what you did rather than just having the grader look into your numbers and find out. This is what she's going to do or he's going to do. I don't know, do we have grader? Yeah, I think. And but at the end, if you explain it, okay, it shows that you understand it. So it's easier in that sense to ignore it if you had numerical errors or mistakes as just final numbers. Okay?
When you use the area, we have the first area. The 2 array need to be very close, right? When you make a calculation.
When you get calculated and the one was given, right? Okay. It's not. I understand. This homework that I did in my graduate course, Dr. Minor. Okay? I'm going to bug you later to see what's going on. Okay? So, no, okay. I understand this misconception in the homework, but whatever you do, if you use the calculated drainage area or the one that was given, I'll give you full point. Okay? Okay. My policy to grade is not too strict. As long as I understand that you did the procedure right, that's all this works.
When it asks us to do
This is what I'm going to talk about today because you have a lot of questions. So okay, from some of the feedback from you guys, I found out you don't know what equation to use and when. And I figured out maybe that's fair. So that's why I uploaded an example in discussion section in Blackboard that I'm going to talk about it today. So just please make sure to have it open because today you're going to understand that EI function, which I believe is ugly, it's so easy. Okay? The simple steps. So again, let me ask you this question. What is EI function again? What is EI function? This form of function. Over here. Okay, so when you talk about time and radius, what do you put in that equation when it is at the well location? You put RW, as simple as that. Okay? Let's imagine that we don't have that logarithmic format of equations. We just have this equation. Okay? and you want to solve it for your well location. So your R over here is RW, and you just put it there and solve it based on solving this EI function. Okay? However, when you have a special condition, you can put logarithmic format. Okay, this is what I want you to understand. So basically, this is what I mean. In a logarithmic format formula, okay, is a special case where you have either very soon time, very early time, or you have RW at the well location. This is to understand it. But what if you have to calculate the pressure 100 feet away from the well? Okay? That logarithmic function is useless. Okay? Why? Because in that case, it is not representing the pressure at the wellbore. Okay? So because we have the class recorded, I'm not able to communicate well to walk. Just please bear with me and try to communicate. Okay? So this is the important fact that you should always remember to use this equation. I'll put too much emphasis, okay, because that's the part of reservoir engineering that it is assumed that you know it after a while. So I just want to make sure it is clear. And in the homework, I asked one question so that you had to use EI function, okay? So I decided to solve a complete version of EI function question to let you know, guys, that it's so simple and it requires a right procedure to follow, and at the end you can get the pressure at whatever T and R.
So EI is the function that gives us the pressure at certain time and distance.
At all time and all radius, as long as the flow regime is steady state, unsteady state.
That's it.
Yeah. So this, put it in your mind as a general definition. Unsteady state is EI function, regardless of the location, regardless of the time, as long as it's unsteady state. But later, okay, as part of this equation, if you are in that location, you can use the logarithmic. But again, in your mind, unsteady state is this formula. Okay?
Which one's the logarithmic?
Okay, let me show that one to you. This equation, no, this is for build-up.
Oh, the one that's like 1.15.
162. You see this one? And it has different. So let me just show it so you don't get confused. So this equation, okay? This equation is just a special case on that EI function, okay? Just know it. If you are asked to give the pressure at the well site location, you see you have RW here. You don't have R, okay? Okay, so let's continue. So please open up the discussion 3 Excel file under discussion folder in Blackboard, okay? So let's talk about the problem that we have here. In this problem, okay, so we have certain information about the reservoir, which is the thickness of reservoir, the permeability, initial pressure, RW, and RE. What is RE? Yeah, radius of drainage area. Okay. So, so before I move on, I have this question. What is shape factor? Shape. What is shape factor that we talked about in the first session when we talked about drawdown test? So shape factor is a constant, okay, that when it is used, certain shape of reservoir can be assumed to be cylindrical, okay, so it's going to have RE as well. So let me be more clear. So you have a square-shaped reservoir. Do we have a drainage radius? No, because it's not circle. Okay, but in general, when we use shape factor, okay, then we can convert it to cylindrical or circle. That the RE concept actually makes sense now. Okay, just something that it came to my mind. It's good to know. So RE is drainage radius. Q is your production, your porosity, your viscosity and compressibility factor, compression volume factor, and you have the time, which is for just equation 1. So again, in this equation, what is unknown usually? It is either T, which is time, or R. So as your friend said, this equation this equation provide an estimation of pressure at whatever time and radius. Okay? So either time or radius should be known, so the other one should be calculated from. See it as a simple equation. Okay? So either T should be known and we can calculate the pressure at different radius, or radius is known to calculate the pressure at different T. So in equation 1, okay, we had the time constant at 3 hours and calculate the pressure at different locations. So basically, let's say you are running an eclipse, okay, and you want to see how pressure changes when you go further away from the well, okay. So you assume that it's going to be the shape of, okay, it's lowest at the well and it's going to increase till it reaches the PI. Okay, for time, for example, 3 hours here. Okay, so we want to calculate that, or actually we want to use this formula, which is the EI function, to get those pressure data for this location. Yes?
Is pressure initial just the pressure at time 0?
Yeah?
So like in the homework, when it said the time PI,
Yeah, you should.
you just take the one that's under.
I mean, I wanted to avoid putting that in because you had to do something else, but I put it, so I already have that point. Okay. Okay, let's move on. I give you a relationship, okay, that this equation works in. So there is a relationship that provides a minimum and maximum value for time where a steady state solution is applicable. So I know that us engineers love to put everything into a either black or white context. Okay? I'm giving you an estimation that if your time is within these two values, most probably you are in your transient zone. So T minimum, what is before it, is Reservoir storage. And what is T max after? After T max is your semi-steady state. Okay? So how to solve this? How to solve this equation? Let me just zoom out. Okay? How to solve this equation? So what is the general procedure that you get to use? Is that this, for example, this term over here is constant because nothing changes, T and R. So okay, you put it here and calculate it. I call it right term, and I calculate it from the given value. So this value is the same. Okay? And we're going to move on, and also, is this value the same or no? I'm trying to solve this equation. I want to make it in an organized way so it can be comprehended well. So for this one, you have everything unless your R. You have T is equal 3 hours, K 4 millidarcy, 18%, 1.5 centipoise, and also you have a compressibility factor. Okay? So And I call this term as mu. Okay? There's a Greek word called mu. Okay? I call this as mu. So I define mu as this parameter, and I put it based on the given r or radius. Does it make sense? Okay? So you just put it here and put your mu over here and calculate it based on different r. So before I go on, for this mu, what? So between r equal RW 1, 10, 20, 100, and 1,000, okay? What do you think this mu is going to be smallest for this corresponding radius? RW, okay? So it is obvious that when you have RW, it should be lowest. And you can see here, mu is lowest. Mu is lowest when you have at RW, and it's just incredibly large when you are far away from your well. Okay? So you have these two values. Okay? Okay. You remember Dr. Gamari talked about x less than 0.01, you have to use something, and if it is above it, you have to use table. Remember? Yeah. So again, let me clear up. You calculated this term, and you are taking care of this term, so you know how to solve this EI function. Okay? Does it make sense? So this EI function, it depends on the value of mu over here. If it is less than 0.01, you use a method, while the other method is different, that you have to read the value from the table if it is more than that. Okay? So that's why I made a separate column for mu. Okay? So I can see which one are less than 0.01 and which ones are more. So the green, it means it is less than 0.01, and for red, it means they are more than that. So let's talk about these numbers over here. For these numbers over here, you get to, how do you calculate EI? So here it is. So if your x or mu, okay, is less than 0.01, okay, so to get the EIX, you just have to use this formula, which is natural logarithm of your mu multiplied by 1.781. Is it clear? Okay. So you have that. You just use this great feature of Excel and do it. So it's going to take care of the other sections or the other radius, which resulted in mu less than 0.01. 0.01, okay? So if you have this EI function, again, and I put it over here. If you have this EI function, you already calculated this, and you have this PI. So you go ahead, use the EI function, okay, and use the constant, and just calculate the PI, which comes out to be 2,748. Okay. This is the fun part. We use just EI function or just EI format to calculate the pressure. Isn't it true that we should expect the logarithmic format also work in this situation? Right? Did you get my question? Okay. What I'm saying is, do you think we got this number over here for PI, for P, using EI function? Since you are very close to well-bore location, do you think that logarithmic format of equation should work? The answer is, let's check it out. Yes. In here, I used that logarithmic format equation, okay, and I solved it. look at how close the numbers came out to be. Okay? They're almost identical. It's the same. You see my point? So now you physically feel that how you use EI and when to expect your logarithmic format formula to work as well. So these two are the same. Okay, let's move on. But what if the x or nu, okay, is more than 0.01? Okay? You use this table over here. It's simple, right? So you have the nu over here. Based on nu, which is x over here, you calculate the DEI. So I calculated for r for nu 0.01, which is going to be in between. Okay, I get the average, which is acceptable approximation. You get the EI function for that nu. Okay, then you put it in this equation, and you get the p. Let's see how different will it be if you use the logarithmic. It's far away. Okay, it's quite different, and it's going to get even worse. Okay, don't use this.
What is the difference between the P and the second P that you have over there?
Okay, this p is calculated using the logarithmic formula, which is only valid for the case where the mu is less than 0.01, which is acceptable for this condition over here. Okay.
What about the other ones?
This one.
No, the other P you have.
Oh, this one. This one is using this function, which at the end I approximated the EI based on natural logarithm of 1.781.
Wait, so how did you calculate the EI for the ones that are above 0.0?
Okay, you use this table. Okay. I'm doing the homework actually. You just have to change the numbers. So if you follow up and you haven't submitted yet, it's going to be easier. So what is x in the table?
For which one?
No, in general. In the table, what is x?
Oh, for x.
It's like nu. I was talking about here. The term inside your EA function is called nu, or x, which is here. So we have 0.15, so we can get it right between these.
If regardless of what method we use, the numbers are very close, how do we, if we're using the other equation with the skin factor, how do we check if x is less than 0.01? Because there's no x on that equation.
Okay, so I'm going to tell you how to calculate the thing. So remember, in logarithmic format, you have an actual scale factor parameter inside the formula, right? Okay. So the pressure drop due to skin, okay, for whatever case, is calculated by using this term. You're using this term here, which is pressure drop. What is pressure drop? Okay, it is 0.87 multiplied by 162.6 Q0 B oil, mu oil, divided by KH. Okay, so this is okay. Dr. Gimari, okay, ask you in the next example that we're going to talk about in build-up test to calculate the pressure drop due to skin. Okay, when we talk about pressure drop due to skin in transient flow, okay, you use this equation, which is 0.87 multiplied by m, which is the slope, and also represent this number. You have to just exchange k and m value, multiplied by your skin factor. Okay, so in general, it's going to be 0.87 multiplied by m skin. You can bring this over here, okay, and put it right over here. because also is, so you see, if you get this one and put it here, it's going to be dp, okay? Total dp is due to this term plus the skin factor term, which is another dp of skin. So, my point is, okay, since everyone used that logarithmic format, okay, they never put skin factor in this sense. Why again? The reason is because sometimes R is further away from RW. In that case, the skin does not matter. Skin is not a factor because we're talking about hundreds of feet inside the reservoir. Okay? So in general, it's not even correct to put a skin factor over here unless they make a exception saying that for x less than 0.01, okay, the format is this plus the skin factor, and for more than that, it's different and there's no skin factor involved. Okay, does it make sense? That's a good question. Does it?
Yeah.
Okay, great.
You are saying, for example, from one of that, you are saying, for example, that you need to define the value of new that you have, right?
If you have to use EI function, right? So you have to calculate mu first, and then calculate the EI function as a function of mu, right? Was it fair to ask that before I giving you this example? Was not? Okay. I think it was. So the material there, but you don't have someone explaining it well. So hopefully you understand it. Okay, done. Is it clear? Is it clear what equations to use and when for unsteady state, and how to actually incorporate the resources or information that you have to solve the DI function?
So for the EI function, the x is just
Mu.
So whatever you get for your mu, you just like over the right,
The table? Yes.
and you just pick that
Yes.
number with the other.
But as long as mu is more than 0.
Is this equation also considered as a way to analyze the inflow performance ratio relationship is unsteady state as well?
Yeah, okay. Good question. So in our IPR curve, okay, what is y and what is x-axis?
Y is pressure, flow rate is your axis.
Okay. So this one is going to be RW for sure. Okay. And so you're going to have different IPR for different times. Okay. So T is going to be specifically known as well. So you put Q, either you calculate Q based on the given PWF or vice versa. So then you can actually draw your IPR curve. Okay, I have put one in discussions. Let me show it to you. Where is this? Here. So look at this. In the first discussion class that we had, okay, I put it over here. Look, this is the IPR curve for on a steady state, but this is the hypothetical case because it's reached over the multi-phase flow case, but still they assume that it's correct. So you see over here, you have different time and different IPR curves for it. Make sense? Here, you see it make sense here? PWF, Q, and this is on steady state with different time. Okay? So, okay, this is what I want you to do.
Can you
Yeah.
go back to for the T not
Is this one? Up?
yeah, the numbers
Here?
Of that, take off to the right. Take
Okay,
off.
okay.
you have the negative E at the
Uh-huh, Yes, yes.
Oh, you want it to be negative?
You have to put it as negative. So this mu is actually minus mu that you were talking about, okay? So yeah, you have to put it as negative. You have to put it as negative, right? The answer is yes. So you have to, I think we have to fix this over here. Yeah, you have to fix it. I forgot to put the negative sign over here. So I'll just correct it and put it again. Okay. So so there was like one critical number which was 0.01, and there is another one which is 10. It means that your mu it goes above 10. Okay. So there is no pressure wave reaching there yet. You just ignore it because your EI function is equal to 0. Okay. So you see, for 100 and for thousands, okay, it's been calculated as 0 because your EI function is more than 10, or your mu is more than 10. Okay, question? I'm happy that you said I forgot to make it, so that's a big deal. So let's okay. You see over here, I made a logarithmic. Semi-logarithmic plot, and as you can see, this is the well location. At well location, you have the lowest pressure, and when you go further away from your well, okay, the temperature builds up till it reaches to the PI, which already was. So, if you ask, have we reached to your boundaries for this case? We say no. Because in this case, the pressure wave has not been felt yet. You see over here, the pressure is the same while you go further away from the well. Questions? No questions? Okay, so I was gonna have you guys do the second part, which is to have the R as the same as RW and calculate T. Okay, please do it at your convenience, because I want to talk about the build-up test. Okay? So it's simple again. So you got EI formula. This time the variable is going to be T, and your R is going to be the same. Okay? You do the same thing. Calculate mu, and then you calculate the EI function, and you get the pressure drop, but for different time. Okay? So let's talk about build-up. So what is build-up?
When you close the well and build the pressure buildup.
Okay. And what information can we get from it? And yes. Drawdown test, yeah. So you can get permeability, steam factor, and you can get the PI. Okay. So this time, okay, let me explain it again. So in drawdown test, okay, you let the oil flow, and then you could calculate the pressure. For the second one, the well is flowing. You shut it down. The pressure stops building up. Okay. So this is vice versa. Again, you can get information from the from the recorded pressure data. Okay. So you have the information over here, and you calculate you have the T, which is given. So these two columns are given by, for example, operator. Okay, but you have to calculate the Horner time. I believe it's called Horner time. You calculate it this way. You get the delta T and just put it there. And what is this T? TP? It's this over here, which is the time of production. Okay, so you put it there and you plot the data. Okay, so in this plot, okay, you plot the Horner time. You plot the shut-in pressure versus the Horner time. Okay, This is just some simple calculations. And then you plot it, okay? You plot it, you get the M from the same way that we discussed, and we can get the permeability out of this equation. Okay, one of the problems or questions that you guys had was, what is one-time cycle? What is one-time cycle that Dr. Gamadi loves to use? Which is convenient. What is it? 1 to 10 or 10 to 100. So log of 100 minus log of 10. How much is going to be? 1, right? What is the log of 10 minus log of 1? It's going to be 1. Okay? These two cycles are the same. So the equation here, which was given, okay, you should be able to calculate it, because in calculus, if you have 2 points, which you have multiple of them, you can get the slope and you can get the intersection. So for the one cycle, okay, so you get the K with no problem, because we already talked about it, how to get the slope. But this time, just make sure that you use Horner time when you're plotting data, and you have to use Horner time to calculate the slope as well. Okay. So Dr. Gamadi here in this file used. Okay, let's see if this number adds up to. Let's calculate this number which was given for PI. Okay, using this equation. Let me see if it adds up. So you see, I'm putting the equation given by. So X, when you're talking about PI, your Horner time is going to be equal to 1. So you put it as 1 plus 3,363.7. Okay, so it's going to be the same. Actually, I don't have to do it, because when X is 1, this value goes to 0. But anyway, so you get the P star, which is an equivalent to PI, okay, which is an approximation, okay. So you go ahead and calculate the pressure at 2 different times, which is going to result in one time cycle, okay. So we calculate for 100, okay, and we calculate for 10. And then we can get the slope from this one cycle. But again, this is just one method. And the one that I discussed in drawdown test is the another one. What are you comfortable with? I'm comfortable with getting an exam, I'm comfortable with getting 4 points and calculate the slope for like 6 times and get the average and report it. It's going to be the same. But Dr. Amadi here used one cycle and used 2 points. And the data is pretty clean over here, so it shouldn't be any problem. 2 points also work. So you get the M, you put M over here, you calculate the K, you use that one-time cycle, you use your actually equation that you got from here, you calculate the pressure at 1 hour, again using this simple equation, you get the scheme factor, and that's all. Okay, drawdown, you have a question?
No.
So when you have drawdown test and build-up test, basically there are 2 independent methods that you can get information from your reservoir. So would you do them? Would you do drawdown and build-up test? Yes, because then I can give more credibility to the permeability that I got from my drawdown, as long as it is the same as the value that you got from your build-up test. Okay? So simply you get that, and again, let's come back to the equation that your friend had. What is the effect of scheme factor? Scheme factor results in pressure drop, okay? So the pressure drop is formulated as this. And when you have the scheme factor, you can just put it in this equation and calculate. Okay? So a question, is it going to be different when it is, let's say, steady state? This equation over here? for calculating the pressure drop due to skin. Is it going to be the same? Yes. Yes. Okay. It's right. Yes. So the skin factor does not care if it is steady state or steady state. Okay. Based on the given production rate, viscosity, formation volume factor, and your permeability and K. Okay. M is always constant. Then you can get the H. Does it make sense? Okay. Okay, let me get over here. So in here, so the dp skin is 0.87 multiplied by ms. What is m? If you transfer k to m, so it's going to be 162.6 multiplied by q oil, b oil, mu oil divided by h multiplied by k. Okay? This variable, when it is multiplied by skin factor, it's going to give you the pressure drop, not due to reservoir or due to the reservoir, just because of the skin damage or skin stimulation that you had. Okay, but fortunately, okay, in this equation, is the skin factor one? The one that has the skin factor, I think I have it over here. Okay, I don't have it. I think it's in another discussion file. But in the logarithmic format, there is one over here that has skin. Okay, that's a skin. If you do a little bit of mathematical simplification, we can get that 0.87 m multiplied by s just from this equation, just taking the s outside. Okay? Okay, any question? So you should be able to do the ER function while the R is not the same as your bell location, right? Yes.
Yeah, on the build-up test analysis graph, why is there a lower storage effect when the time is over 1,000?
Okay, when you're talking about corner time, okay, it's case vice versa. The beginning, so the beginning of the shutting experiment or shutting operation is going to have the highest corner time, okay? When time goes by, let's say 2 days, that corner time equals to 1. So the sequence is reversed this time. So you don't see it as time. See it as another variable, which is corner time. Questions? No questions? Good.
For the,
Yeah.
I guess for the homework for today, that Q that you gave us, is that the Q max or
Which one? Talking about the third one?
The ones that you
No, I understand, but is it the Vogel one or not? No?
yeah, whatever.
It was Vogel? Okay. So you remember for the Vogel, you were required to have 1 point, okay, from actual data to construct your IPR curve. Okay, that's the point.
Oh,
So the PWF is associated with that Q that was
oh, okay,
given.
so that's.
Okay, no more questions? Okay, so I hope you understood something. Class dismissed.